Hi, I'm Conor Houghton, and this is lecture 7 in the information theory section of our unit Information Processing and the Brain. This lecture, which will be a very short one, is about the differential entropy. It's just going to introduce the differential entropy, give a couple of examples, and I'll talk a small bit about it. There'll be a follow-up lecture where I talk a little bit more about it. So, the differential entropy. The business of the differential entropy is continuous probability distributions. So here to with, we've been dealing with discrete probability distributions. We have some set of outcomes, x1, x2, up to xn. They're discrete individual outcomes. And for each of those, we have a probability, p of x1, p of x2, up to p of xn. That's how a discrete probability distribution works. We have some discrete outcomes. We have probabilities on those outcomes. The probabilities obviously have to satisfy the properties that probabilities have to have. They all have to be positive. They have to add to 1. But the key point is that we have a discrete space. But many of the problems that we want to deal with, that we want to model with probabilities distributions, will have a continuous sample space. You know, measurement problems, how long things are, how tall things are, how much things weigh. Measurement problems, where something is in space. Measurement problems will take their values in a continuum. In other words, the sample space will be some subset in most cases of r to the d, although obviously more exotic possibilities are possible, you know, complex numbers or whatever. But that doesn't introduce all that many extra complications. The main point is for continuous probability distribution, the sample space is some subset or all of r to the d, where d is some dimension. Mostly in the examples we're looking at, and both examples we look at, d will be 1. So the probability distributions on continuous spaces are actually quite different, and they're quite different because in the discrete case you have the probabilities. You have x1 up to xn, and you have p of x1, the probability of x1, p of x2, the probability of x2. In the continuous case, you don't have that because, of course, the probability of a single point is 0, of getting a precise value is 0, because of course points have an infinite precision. You know, maybe there's some probability of getting 1.1001, but what you actually have is 1.1001000000. It's just like when you weigh something. If you're weighing an object has mass, but if you weighed an individual point, it would have no mass. The mass comes from integrating the density of the object over its volume, and the same is true of continuous probability distributions. I know I'm telling you things that you already know, but it gives us a run-up to the business of today, which is the differential entropy. So in the continuous case, you have a probability density instead of a probability. Here is just the example of the Gaussian. This is p of x, and this is the probability density for that distribution. And the set of allowed values here extends over the whole of the real line, although if you get far away from the center of the probabilities, it becomes extraordinarily low. And so the density is the thing that you integrate to give the probability. So the probability of getting a value inside this region between x0 and x1, well, that's just the integral of the density over the region. It's the area under the curve. So as I said, it's just like you have, just like the case with matter with variable density, the mass is calculated by integrating the density. A probability density is much the same. The thing you're interested in, the probability, is calculated by integrating the density. The difference, of course, is that the integral over the whole of the sample space, the whole of the allowed region, has to be 1 for a probability density, just because the probability of the value that you choose lying in that region also has to be 1. So that's the probability density. Now we want to extend the ideas of what we had before about Shannon's entropy, ideas that we explored in the discrete space. We want to extend those ideas into the continuous space. And you know, when you're going from discrete to continuous, this is kind of a thing you always do, which is you guess that all that happens is you take any sums you might have and you replace them by integrals. And so the idea we might have is that we would do the same thing here. So before we had big H of x is equal to minus the sum of p of xi log to the base 2 of p of xi, and so we take that sum and we replace it with an integral. But the slightly confusing thing is that we have to make a further guess, which is that we had probabilities in that integral, P of xi, and we don't have probabilities here, we've got probability density. So we're also going to, in our guess as to what a differential entropy formula might look like, what a formula for the entropy on a continuous distribution might look like, we'll also guess that those probabilities get replaced by densities. And so this, in a sense, is sort of the obvious guess as to what the continuous distribution version of Shannon's entropy should look like. But you'll notice that before we had a big h of x, and we're using a little h of x here. And that's because this is really a different object, because it's not the expected value of the log of the probability, it's the expected value of the log of the probability density. And the probability density, although obviously related to the probability, is not the same thing. And this object is not the same object. The Shannon's entropy, we discovered that Shannon's entropy had lots of nice properties. You know, its boundedness by 0 and by the log of the number of elements, the fact that its relationship with the source coding theorem. These gave us sort of confidence that it was the right object. It was the right object for measuring the information content of the outcome of a random variable. We don't have those, well, we haven't yet tried to find those same properties here. And in fact, what we'll discover is those properties are absent. So this guess here has given us a formula for the information. It isn't in the way that the Shannon's entropy is. It isn't bounded or founded or justified by a relationship to the source coding theorem or boundedness properties. There are other properties of this object, the differential entropy, that we won't have time to go into in this unit, but I do recommend them to you. These are the channel capacity theorems that are kind of an analog of the source coding theorem. So this differential entropy is, I mean, as I said, it's the kind of the obvious guess as to what the entropy for a continuous distribution might look like. We'll see very shortly when we look at the examples. It lacks some of the nice properties that Shannon's entropy had in the discrete case, but nonetheless it'll turn out to be a useful object, not least because of its relationship with the mutual information for continuous distributions. And the mutual information, as we'll discuss, is a lot closer to the mutual information in the discrete case than the differential entropy is to the Shannon's entropy. The differential entropy, as indicated by the little h, is a different object. Anyway, without further ado, let's do a couple of examples. So, you know, this is the uniform distribution. It's the sort of most obvious example. The uniform distribution tells us that it models a random variable that takes its value between 0 and a, and is completely even between 0 and a. And of course, the area under this curve has to be 1. So if the if the compact support is from 0 to a, and it's flat on top, then the height has to be 1 over a to give the correct probability of getting a value, which has to be 1. Said too much about that now. Let's quickly go on and work out the entropy, the differential entropy for this distribution. And it looks like this. You just take the probability distribution and you shove it into the formula for the differential entropy. This is the formula for this differential entropy. We put the p in. Basically what it says is that the support is between 0 and a. So where it was minus infinity to infinity, we replace that by 0 to a. And then inside that support, provided x is in 0 to a, the p of x is equal to 1 over a, so we can take it out here. This is also a constant. We're just left with this integral here that integrates to a, cancels with the 1 over a here. The log to the base 2 of 1 over a is minus log to the base 2 of a, there's a minus there, and so we get the differential entropy is equal to log to the base 2 of a. So on the face of it, that looks quite nice. We start off with the uniform distribution, arguably the simplest continuous distribution, and we ended up very quickly with a formula for the differential entropy. The problem with this formula is illustrated in this picture here. So this is a plot of the log to the base 2 of a. This is a along here. This point here is when a is equal to 1, and at that point h of x is equal to 0. And so for any value of a less than 1, we're going to get a negative number. And so we quickly see that the differential entropy lacks one of the key properties of Shannon's entropy. It's not a positive. It's not always positive. It can be positive and negative. And you can also see that as A gets bigger, as the thing gets wider, the differential entropy goes off to infinity. Now, you could try and argue that that was the same as the log to the base 2 of n going off to infinity, as the number of possible outcomes went to infinity. But those arguments get sort of quite confusing and complicated. Just before we go on to talking a little bit more about that, I want to do the other sort of common example, which is the Gauss distribution, the curve we saw earlier. So when you think of continuous distributions, the first one you think of as uniform, the second one you think of as normal, and then you might think of the other ones after that. So this is the Gaussian distribution. For simplicity, I've set the mean to 0, and you can shove that into the formula as before, and if you look, the log bit will give you the log of an exponential, which will roughly give you this bit here. Because it's a log to the base 2 and this is an exponential, you'll get an extra e coming out here. E is is just the exponential of 1. So if you shove this in and then integrate by parts, so you'll get an x from the log bit, and then you get an exponential itself. So you have to integrate by parts. One of the great problems of setting exam questions, for example, in probability theory or subjects based on probability theory, is that they so often come down to asking, can you integrate by parts? And this is another example. Working out the differential entropy here is a matter of integrating by parts, but if you do integrate by parts, you get a formula for it, which is that the differential entropy of the Gauss curve is a half the log to the base 2 of 2 pi e sigma squared. And the same thing is true. If sigma is small enough, then h of x, well, sigma is smaller than 1 over 2 pi e, to be precise, then h of x will be negative. Basically what we're seeing, and we will talk about this some more, is that as you kind of expand these distributions, you have some transformation of the distribution that comes by sending x to a times x, and you make it bigger or smaller if a is greater than or less than. As you do that, you change the size of the distribution, and morally, is that the thing that you want to measure? It's not so clear, but what is clear is that you can prove that easily, and we'll talk about that the next day, is that when you do that transformation, if you expand your distribution, so in the case of the Gaussian, that would mean making it flatter and wider, and the same is true of the uniform distribution, if it wider, but lower, because this is a across and 1 over a. As you do that, you make the information larger. So to talk about the largest entropy, the highest entropy distribution, the analog of the uniform distribution in the discrete case, well, that's not so easy to do, because as I said, you can always increase the entropy of a distribution by this transformation that preserves the area under the curve, but expands it, makes it wider, and therefore flatter. So talking about the highest entropy is not sensible unless you fix that family of transformations, which you can do by fixing the variance of the probability distribution. And weirdly, unlike the discrete case where the highest entropy was given by the uniform distribution, in the continuous case, the highest entropy is given by the Gaussian. So for fixed variance, the Gaussian distribution has the highest differential entropy. So why is the differential entropy so much different to the Shannon's entropy? Well, in the next lecture, we'll explicitly calculate how to derive one from the other, and that will give us a good understanding of what's going on. But just to finish off this lecture, I just wanted to say a little bit about why the differential entropy, you'd expect it to be a different case where things are different, and the nice things that have worked before might not work this time. For a start, I've mentioned this before, the discrete case, we're dealing with probabilities. Here we're dealing with densities, and so we have changed the object inside our formula. That's the first point. another point is that, and again we will deal with this more explicitly in the next lecture, the intuition we had, which is that when you're going from discrete to continuous, you change integrals to sums. That doesn't deal with the fact that we actually do have a probability here that's inside the log, and so the entropy formula does have a probability inside the log, and you're changing something inside another function from a. You might say, well, it doesn't really matter that much, the difference between the probability density and the probability, because if you integrate the density, you get the probability. But integrating is kind of what you're stating there is a kind of linear property. If you integrate the probability, you get the density, you get the probability. But this density here isn't so well. It's inside a log, and so you can't get to it in a linear fashion, as it were. So we have no real right to expect the differential entropy to be the same object as the Shannon's entropy, to be the continuous version of the Shannon's entropy. But beyond that, there is an issue with the basic quest, which is that we're asking how much information is there in a continuous signal, and in a sense, the answer has to be infinity, because giving you the precise value of a continuous variable gives you an infinite amount of information, because the continuous variable, the value of it, has an infinite number of decimal digits in its expansion. So if I told you what value x took if x is a continuous variable, then I'm giving you an infinite amount of information. No matter how much you might expect the first 1,000 digits, you might not expect to be able to predict the next 1,000 digits. There's the continuous numbers are like really infinite. They from counter diagonalization arguments and so on that that there's just an awful lot of real numbers. And so if you have a continuous probability distribution and you know a value of the probability distribution, that is, to describe that value would take an infinite number of bits, because the digital expansion, or the expansion, goes on forever. And so the whole idea of assessing the amount of information in a continuous variable seems bankrupt from the start. Now, my argument is true. I mean, that's a true argument. But your intuition is probably that I'm also kind of missing the point. If we're using these continuous distributions to model measurement problems, to model real life problems, to do something useful, then in those real life problems, we're never actually going to measure all of the digits in the decimal expansion anyway. So I might say, if you have a continuous distribution and you know a value from the continuous distribution, describing that value takes an infinite number of bits, because it's a real number. But we know full well that for exactly that reason, this isn't a useful model of an actual measurement process. If we're trying to measure, the process of sending a communication by a radio signal that fluctuates up and down, you might say, well, that radio signal is, its amplitude is fluctuating up and down, and so that's an infinite amount of information, because to describe the amplitude at a given time, you need an infinite number of bits to say precisely what the value is. But we're never going to measure the radio signal with that precision. We're never going to measure the amplitude of the radio signal to full precision. I mean, both because during the transmission there will be noise added to the radio signal, and because our measurement device is not going to make that infinitely precise measurement. And so, that's illustrated here by showing that this number, well, in practice we're only going to use the first couple of digits of that number. Only the first couple of digits are going to be free from noise. Only the first couple of the digits will be measurable by whatever device we're using to measure the signal. In the radio example, you have the person sending out the information using their radio. You think, well, they only need to send out one instant of radio signal, because the amplitude of that radio signal will contain an infinite amount of information. But we know that in practice that's not true, because the receiver, the radio receiver, will not measure that with arbitrary accuracy. So we need to deal with this continuous problem, the issue of the information in continuous signals. We need sort of a model of the sensitivity of the receiver as well as the behavior of the source. So here's kind of a cartoon here. We have this here is the this is X, this is the distribution the values are being drawn from, and it's supposed to be this blurry thing which represents a Gaussian. And so a point, this is a point that's drawn from this distribution, and I've drawn it as a little disk, but it's a continuous distribution for this point. In principle has arbitrary accuracy, but in practice, when we receive it, it'll be received with some noise and with some blunted precision in the description of the value that's received. And so the receiver receiving the information that's been encoded in this point, which is drawn from this distribution, won't have access to the precise value of or location of that point, but will have some sort of noisy measurement of that point. And indeed, if there's 2 points received, there's an issue about how well they can be distinguished, because they overlap or near overlap. And so what you're dealing with now is you have the original distribution, the thing whose information you might be interested in, and then you also have this sort of the model of the noisy transmission and imprecise measurement of that signal. And so what you're dealing with here is not, what you actually want is not a differential entropy. What you actually want is the mutual information for continuous random variables, because what you'll be interested in is in modeling real world problems with probability distributions is not the continuous variable on its own, but the continuous variable plus the measurement that's made of the continuous variable. And that, as I said, is the realm of mutual information. And what we'll discover is that while the differential entropy lacks some of the nice properties that the Shannon's entropy has, the mutual information on continuous variables in fact has precisely the nice properties that the Shannon, the original mutual information had. So that's it. Thank you very much.